right, so now we're going to be graphing rational functions where the degree of the numerator is less than the degree of the denominator, but we have polynomial parts, meaning we have something raised to a power other than 1, and where the degree of the numerator is the same as the degree of the denominator, but this time where we have polynomial parts where one of our x's is raised to some power other than 1. So these two I put all together. All right, so let's review our steps, and the steps are in your notes. So rational functions and their graph where n is less than m. In other words, the numerator has a smaller degree than the denominator, or where they have the same degrees, but we have polynomial parts. All right, so number one step that we haven't had to do before is to factor first. So set each factor of the denominator equal to 0. These functions can have more than one vertical asymptote, so we may have vertical asymptotes. Each value which makes the denominator equal to 0 is going to be a vertical asymptote, so long as it doesn't cancel out. And then in these particular graphs, we're not going to have any factors that cancel out. There can be no vertical asymptotes if we have a continuous function. Right, so our vertical asymptotes are the values that make the denominator equal to 0. After everything that can be reduced has been reduced, and these particular graphs won't have anything to reduce. And then horizontal asymptotes, the rule is exactly the same. It doesn't matter that we have x's raised to a power. If the numerator has the smaller degree, right, so n is for numerator, m is for denominator. If the numerator has the smaller degree, then our horizontal asymptote is y equals 0. If they have the same degree, it's still the ratio of the coefficients in front of the leading term. We're going to find the x-intercepts. They are the real zeros of the numerator, so we just set the numerator equal to 0 and solve for x. If you haven't noticed, when we cross multiply and you multiply anything by 0, you get 0. So all that really matters is that the numerator is equal to 0, because when the numerator equals to 0 is equal to 0, the entire fraction is equal to 0. To find the y-intercept, you just set x equal to 0. You're going to plot 2 or 3 points on either side of a vertical asymptote. These can include the x-intercepts or positive and negative values substituted for x, or the y-intercept. Factoring the numerator allows you to recognize the x-intercepts. If there are 2 vertical asymptotes, you must find 3 points between the asymptotes for 7 points total. Right? So you need to have 7 to 9 points total if you have 2 vertical asymptotes. Right, so and we're going to go through all the steps again, and really the only thing that's different is we're going to have to factor first, and our graphs might be slightly more complicated, and just slightly. We're going to determine the domain. Values that make the denominator of a fraction equal to 0 are not included in the domain of a rational function. So you're going to exclude vertical asymptotes from the domain. Everything else is fine, but you're going to exclude the vertical asymptotes. Rational functions where x is raised to a power may cross the horizontal asymptote, or may turn around and exclude some values in addition to the horizontal asymptote. You're going to have to use the graph of the function to find the range. So these graphs are a little bit more complicated. You're not going to just take out the horizontal asymptote to determine the range. Right? You're going to have to look at the graph first. Right, so let's go through our steps. Here's our first one. All right, so we have y equals x divided by x squared plus 1. This is this is a sum of squares in the denominator. That is not going to factor. All right, so factoring first, we have nothing to factor. So here, this is an NA. All right, because there's nothing to factor. All right, so if we try and set x squared plus 1 equal to 0, we would have x squared equals negative 1. And if we take the square root, and don't forget, always plus or minus if we have something squared, or something to any even power, and we take the square root of negative 1, square root of negative 1 is I. Right? So since the solutions are complex, there are no vertical asymptotes. Right? So we don't have any vertical asymptotes. To find the horizontal asymptote, you look at the degree of the numerator and the degree of the denominator. Right? So the degree of the numerator, we have an x. Right? So that would be degree 1. This is raised to the first power. In the denominator, we have an x squared. That's degree 2. Right? And 1 is less than 2. Since the numerator has the smaller degree, y equals 0 is the horizontal asymptote. Right? So here n is less than m. The degree of the numerator is less than the degree of the denominator. So y equals 0 is the horizontal asymptote. By the way, I believe this one's in the notes, but I do not have the notes in front of me. So just follow along and look and see which of these problems are in your notes. All right, so we want 2 or 3 points on either side of a vertical asymptote, but we have no vertical asymptotes. All right, so since we have no vertical asymptotes, we're going to plug in 2 positive and 2 negative. And, of course, 0. All right, so if we, and actually, did I give myself room on the next page? Yeah, I did. So I'm not gonna do that over here. We will do this on the next page. And then the domain, if we have no vertical asymptotes, the domain, as you're going to see, is going to be all real numbers, right? Because the domain is everything except what makes the denominator equal to 0. Since no real number makes the denominator equal to 0, our domain is going to be all real numbers. We're going to have to look at the graph for the range. All right, so let's write down our vertical asymptote, which is none. The horizontal asymptote is y equals 0, so we'll graph that. And let's create our table of values. All right, since we have no vertical asymptotes, let's take -2, -1, 0, 1, and 2. Right? 2 positive, 2 negative, and 0, which is going to be both our x and our y-intercept. All right, so if we plug in -2, we have -2 divided by -2 squared plus 1. That's going to be -2. That's going to be 4 plus 1, so that's -2 fifths. And then we have -1 divided by -1 squared plus 1. That's going to be -1. -1 squared is 1. 1 plus 1 is 2, so -1/2. So this, by the way, as you're going to see from the graph, is our largest value, because -2 fifths is smaller. If I plug in 3, I'd get something even smaller. I'd get -3 divided by 10. -3 tenths is smaller than -2 fifths, right? Because 2 fifths is 4 tenths. And so now our values are just going to keep getting smaller. So if I chose larger values than -2 and 2, I'd have smaller values to graph. If we plug in 0, we're going to have 0 in the numerator, so 0 divided by 0 squared plus 1, that's just going to be 0. If we plug in 1, we have 1 divided by 1 squared plus 1, that's going to be 1/2, same values except for the sign. And then if we plug in 2, 1 divided by 2 squared plus 1, that's going to be, oh, excuse me, we're plugging in 2, not 1. That's going to be 2 fifths. So let's graph our values here. You can see we are crossing the horizontal asymptote, right? Because we have 0. We have y equaling 0. So we have the points -2, -2 fifths. So not quite a half. We have the point -1, -1/2. It's a little bit more. We have the point 0, 0. We have the point 1, 1/2. And then a little bit smaller, we have the point 2, 2 fifths. Right, so our graph is going, it has no vertical asymptote, so we have all real numbers here. Notice that as we come from 0, we have our big maximum value there of -1/2. I guess I should say our minimum value. Our big minimum value there of -1/2. And then our function heads right straight back to the asymptote, because it has to. Right? The asymptote is what the function does as x gets larger and larger or smaller and smaller. The same thing happens on this side. It's like a mirror image. Right? We got our big maximum here of 1/2, and then we head straight to the asymptote. So this is one of our more unique graphs. Like I said, we can get some different shapes here once we start adding something squared in our denominators and numerators. Right? Our denominator has to always be positive, but our numerator can be negative. And we have no vertical asymptotes, and so it creates this shape. Our domain is all real numbers. Nothing I can't plug in there. Right? Not going to get any imaginary numbers there. Not going to have any zeros in a denominator. Nope. And the range, well, if we look at our graph, we have our small value of -1/2 and a maximum value of 1/2. So our entire graph just fits in there between -1/2 and 1/2. The last thing to do is to find the end behavior, and this is a pretty easy end behavior. We don't have any vertical asymptotes, so it's just what does the function do when it heads to -infinity, infinity. F of x approaches 0 as x approaches -infinity, and it approaches 0 as x approaches infinity. It has to, because 0 is the horizontal asymptote. And that's it. We're all done with this one. Right? So this one took a little longer, but we did go over the steps for graphing. Here's our next one. Factor first. Again, nothing really to factor here. We have a sum of cubes, but we can set our denominator equal to 0 and solve. So we have x cubed plus 1 equals 0. If we subtract 1 from both sides, x cubed equals -1. When you have an odd power, you don't need there's no plus or minus. If I raise a positive number to an odd power, I'm going to get something positive. If I raise a negative to an odd power, I'm going to get something negative. No imaginaries here, no complex numbers. So we just take the cube root of x cubed and the cube root of -1. Cube and cube root cancel, and the cube root of -1 is -1. So x equals -1 is the vertical asymptote. We have one vertical asymptote. And you're going to find this particular graph, even though we have an exponent, is not going to look a heck of a lot different than the graphs we've been doing. Let's find the horizontal asymptote. We find the horizontal asymptote by finding the degree of the leading term in the numerator and the leading term in the denominator and comparing. All right, so we have a -1 is the only term in the numerator. That is degree 0, because there's no x's. Right? So having a constant is the same as having x to the 0 power, which would be 1. The degree of the leading term in the denominator, we have an x cubed, so that's degree 3. Of course, 0 is less than 3. So the numerator has the smaller degree. Our horizontal asymptote is, again, y equals 0. All right, so we've got one vertical asymptote. We'll plot 2 or 3 values on either side of that vertical asymptote. The domain is going to be all real numbers except for the vertical asymptote, and we're going to have to look at the graph to find the range. And you know what we should do over here? Since we have this nice big space over here, let's find the x and y intercepts. In the other graph, it wasn't all that interesting. It was just going to be 0, 0. And so if we set, to find the x-intercept, you set y equal to 0. So 0 equals -1 times x cubed plus 1. If you were to cross multiply, you get 0 times x cubed plus 1 equals -1. Right? So notice you just end up with 0 equaling the numerator every single time. Right? Right? But if it's easier, you can just cross multiply. You'll always get 0 as one of your products, and then whatever the other product is. But 0 equaling -1, that's not a true statement. So there are no x-intercepts. How about y-intercepts? Right? So to find the y-intercept, you just plug in 0 for x. So we have y equals negative 1 divided by 0 cubed plus 1. Well, that's just going to be negative 1 over 1, which is negative 1. So we do have a y-intercept, and that's 0. We plugged in 0 for x, and we got negative 1 for y. That's one of our points. Right? So we've already got 1 point. We need at least 2 or 3 more points on either side. Right, so vertical asymptote is x equals negative 1 and there we go. Horizontal asymptote was y equals 0. And we'll plug in, and we already have one value. Right? When x was 0, y was negative 1. Right? So we've got one value on the right-hand side of the graph. Let's plug in 1 and 2. I'm going to move it down actually just a little bit. So we'll plug in 1 and 2, right? And then less than negative 1, we'll plug in negative 4, negative 3, and negative 2. And actually, this is a pretty simple graph. Yeah, we'll plug in that. We'll plug in this many. It's all right. So, because this is actually pretty easy on the computation. Negative 1 divided by negative 4 cubed plus 1. All right, so that's just going to be negative 1. That's going to be negative 64 plus 1, so that's negative 63. I don't even know why I bothered. That's really going to be kind of small. So you know what? Since that is so small, I don't even think I can graph that very well. Let's, instead of using 3 values on either side, let's use our minimum, which is, oops, my eraser's in the wrong spot. Let's just use the minimum, which is 1 value on each side, because I think these values are going to get, or excuse me, 2 values on each side, because I think these values are going to get really, really small. All right? So the minimum is, if we have one vertical asymptote, is 4 points. Right? So we'll just use the 4 points, because I don't think I can graph negative 1/63 very well anyway. So we have negative 1 divided by negative 3 cubed plus 1. Right, so that's going to be negative 1 divided by negative 3 cubed is negative 27, plus 1 is negative 26, and so that's 126. That's pretty small as it is, but I need at least 4 points. If we plug in the negative 2, we get negative 1 divided by negative 2 cubed plus 1. So negative 2 cubed is going to be negative 8. Negative 8 plus 1 is negative 7. So this is going to be negative 1 over negative 7, or just 1/7. We've got 0, negative 1, our only nice value. And then we'll plug in 1. Right? So we have negative 1 divided by 1 cubed plus 1. Right? Well, that's going to be negative 1/2. Right? So there's our 4 values. Let's graph those. Right, so we have negative 3, 126. So just make it, or excuse me, positive 126. Just make it really close. Now I got a red dot on my asymptote. Okay, here we go. Just make it like really close. As close as you can make it. All right, 1/7 is just a teensy bit more. Okay, on the other side, we've got our nice value of 0, negative 1, and then 1, negative 1/2. So notice it pretty much has the same shape. It will not cross the vertical. It cannot cross the vertical. Oops. It's not supposed to cross the horizontal. There we go. Same thing over here. It won't cross the horizontal, and it cannot cross the vertical. All right? So kind of the same shape. It's just these values got really small really, really fast. So the domain is everything but the vertical asymptote, negative infinity to negative 1, negative 1 to infinity. The range is everything but the horizontal asymptote. So if you have an exponent, but it's to an odd power, it's really going to look pretty much the same as the graphs we've been doing, except you might get some really tiny values. So the range is negative infinity to 0, and 0 to infinity. Let's do the end behavior. All right, so as we approach negative infinity, f of x approaches 0 as x approaches negative infinity. As we get closer to that vertical asymptote, our function is going to grow without bounds. So f of x approaches positive infinity as x approaches -1 from the left. And it's the reverse as x approaches -1 from the right. So f of x approaches negative infinity as x approaches -1 from the, there we go, right-hand side. That's a little sloppy. Let me see if I can make that just a little neater. And then as f of x as x approaches infinity, f of x again approaches 0. Our horizontal asymptote. There's something wrong with my black. This is a black pen I'm using to write with. There we go. It's, I don't know, it's sticking. All right, so f of x approaches 0, a horizontal asymptote as x approaches infinity. And we're finished another one. All right, so that one wasn't too bad. So the 4 points, by the way, is the minimum, and you can only do that if you have only one vertical asymptote. This function has 2 vertical asymptotes. This is an easy factor, though. We have a difference of squares in the denominator. So we can just factor that. It's going to be square root minus square root, so x minus 2 times square root plus square root. So x squared minus 4 factored is x minus 2 times x plus 2. All right, we have to set both of those factors equal to 0. So if x minus 2 equals 0, x equals 2 is one vertical asymptote. If x plus 2 equals 0, x equals -2 is the other vertical asymptote. For the horizontal asymptote, just compare the degree of the numerator and the denominator. So the leading term in the numerator is an x. That is degree 1. The leading term in the denominator, and the leading term is not necessarily the first term. It's the term with the largest exponent. So the leading term in the denominator is x squared. That's degree 2. Right, so 1 is less than 2, which means the numerator has the smaller degree, which means y equals 0 is still the horizontal asymptote. On this page over here, let's find the x and y intercepts. To find the x-intercept, so notice that if I plug in 0 for y, oops, that's supposed to be an x, what the heck happened there? If I plug in 0 for y and cross multiply, every single time I'm going to get whatever's in the denominator being multiplied by 0. So anytime I multiply by 0, we're just going to get 0. Right? So it is okay if you just set the numerator equal to 0. So x equals 0 is the x-intercept. And when x was 0, y was 0. Not only is that our x-intercept, it's our y-intercept. And you can see if you plug in 0 for x, you're going to have 0 over -4, which is 0. So the x-intercept and the y-intercept is the point 0, 0. So that's going to be one of our points. And obviously we cross the horizontal asymptote because the horizontal asymptote is y equals 0. The domain is going to be all values except for the vertical asymptotes, and we're going to have to use the graph to find the range. So let's go to our graph. All right, so we have the vertical asymptote, 2 vertical asymptotes, x equals 2 and x equals -2. Let's graph those. Okay. And then the horizontal asymptote is y equals 0. We need points on either side of those asymptotes, and we need 3 values in between the 2 asymptotes. So 2 values will be enough for me to the right and to the left. So we'll use -4 and -3. Between the 2 vertical asymptotes, we're going to have to use -1, 0, and 1. Fortunately, we've got 2 integer values, and we actually already know one of those because when x is 0, y was 0. And then we're going to need 2 values that are greater than the larger vertical asymptote, so 2 and 3. All right? And so we'll plug those in. So we have -4 divided by -4 squared minus 4. So that's going to be -4 divided by 16 minus 4. 16 minus 4 is 12, and that reduces to -1/3. So I'm not going to write. I'm going to do a little bit of this in my head, but I'll vocalize what I'm doing. And if you have any questions, just let me know. All right. So now we have -3. We're plugging -3 everywhere we see an x. -3 divided by -3 squared minus 4. So that's going to be -3. That's going to be 9 minus 4, which is 5. If we plug in -1, we've got -1 divided by -1 squared minus 4. That's going to be -1, and that's going to be 1 minus 4. So that's going to be -3, and that's just a +1/3. All right, we've already got the 0. All right, so now we have, when I plug in 1, we've got 1 divided by 1 squared minus 4. I'll make that a little neater. That's going to be 1 divided by 1 minus 4, so that's going to be -1/3. So just the opposite of what we got when we plugged in -1. If we plug in 2, we have 2 divided by 2 squared minus 4. Wait, did I plug? Yeah, okay. Making sure I plugged in the right value there. Oops, 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 oops. Why did I put a 2 here? I did not mean to put a 2, 3. I meant to put a 3, 4. There we go. Can't use 2. 2 is our vertical asymptote. We would have gotten 0 over 0. That's no good. All right, so, or not 0 over 0. We would have gotten 2 over 0. Either way, not any good. All right, so let's use 3 like I meant to. So we have 3 divided by 3 squared minus 4. That's going to be 3. 9 minus 5, that's going to be 3/5. So notice, just the opposite as what we got when we plugged in -3. That's because the denominator is when it's greater than 2 is always going to be something positive. The numerator is just whatever value we're plugging in. And then finally we have 4 divided by 4 squared minus 4. Sorry, that's a little bit crammed in there, but I don't think you'll have any trouble figuring out. That's just 4 over 16 minus 4. That's just the same thing as we got before, but positive. So 4/12 or 1/3. So notice this is a very symmetric graph. Let's graph the points. So we have -4, -1/3. It's about there. -3, 3/5 is a little bit bigger, so this is going to be a little bit more in the negative direction. Oops. It should actually be bigger than that. 3/5 is greater than 1/2. Let's see if I can get that out. There we go. All right, so it should be more than 1/2, like right there. All right, so, and then in the middle there, we've got the point -1, 1/3. So about there. We have the point 0, 0. And we have the point 1, -1/3. So if you notice, these are going in a diagonal. If your points go in a diagonal like this, they're going to be S-shaped. In the middle, when we have 2 vertical asymptotes, the middle part is either going to look like an S or look like a U. That's why we need 3 points. If we only had 2 points, we couldn't tell if it was going to look like an S or look like a U. And then we'll plug in the point 3, 3/5. And the point 4, 1/3. Right? So to the left will not cross the horizontal, will not cross the vertical. Looks like that. To the right, basically a mirror image, will not cross the vertical, will not cross the horizontal. Looks like that. It's in the middle that we're a little bit different. In the middle, we cannot cross that vertical asymptote. We will cross the horizontal asymptote one time, and then we will not cross the vertical asymptote. So we're going to have an S in the middle. So when you've got two vertical asymptotes, you might have an S in the middle, you might have a U in the middle. And what's going to tell you is you just have to look and see, are your points making an S or are they making a U? And that's why we're going to always need 3 points in the center. The domain is everything but the vertical asymptote. So negative infinity to negative 2. So we're skipping over negative 2. We have to skip over 2. So now we're going to have 3 parts. So negative infinity to negative 2. And then negative 2 to 2. And then 2 to infinity. Literally everything but the vertical asymptotes. The range, notice we didn't cross the horizontal asymptote if we look to the left. We didn't cross the horizontal asymptote if we look to the right, but right in the middle, we've got that part that went right through the horizontal asymptote. And you can see that part's going to keep increasing on one side and keep decreasing on the other. So the range is all real numbers. So sometimes we have x's raised to powers, we might have a range of all real numbers. The last part we're going to do is the end behavior. I'll try and do that quickly. We've got a lot of end behavior here because we've got 2 vertical asymptotes. So f of x will approach 0, the horizontal asymptote, as x approaches negative infinity. As we approach the first vertical asymptote, negative 2, f of x approaches negative infinity as x approaches negative 2 from the left. That's what makes it a vertical asymptote, that our function is going to go to infinity or negative infinity as we get close to that asymptote. And then f of x is going to approach positive infinity as x approaches negative 2 from the right. Right? And now we look to the other vertical asymptote. This time f of x is approaching negative infinity as x approaches 2 from the left. Positive infinity as x approaches 2 from the right. And f of x is going to approach 0 as x approaches infinity, because that's our horizontal asymptote. And this looks like a good place to stop. All right, so we're going to stop with this graph. So far, we've just had the numerator with the smaller degree. And the next podcast, we may see some where they have the same degree. Thanks for watching. Bye for now.